we're going to look at the intersection of three planes. Consider these three equations. If I add these two equations, I eliminate z and obtain this equation here. Now normally I would leave that as it is, but for the purpose of this demonstration I want to change it into the form y equals mx plus c. Adding equations 2 and 3, again we eliminate z and obtain this equation, and in y equals mx plus c form it is this. Now solving those two equations we get x is 4, y is 3, z is 4, and the intersection point is 4, 3, 4. This diagram shows the three planes, the intersection point 4, 3, 4, and the actual lines of intersection of the three planes. Now I've just taken away the three planes themselves and just left the intersection lines. Now I'm not going to be using this one, so I'm going to take that one away too. The green line is the intersection of the planes 1 and 2, and the turquoise line is the intersection of planes 2 and 3. Looking at the green line with the planes themselves, the equation of the green line is quite complicated. In fact, it can have three forms. It can be written as a vector equation, or a parametric equation, or in Cartesian form. However, we don't actually use the equation of the intersection of the planes in the working. But when we added the equations 1 and 2, we got this equation y equals negative 3/4 x plus 6. And the question is, what does this actually represent? It's not the line of intersection of the planes 1 and 2, because that was the complicated versions on the previous page. Thinking laterally, we could say that y equals negative 3/4 x plus 6 is just a line in the xy plane with a gradient of negative 3/4 and a y-intercept of 6. If we now draw the orange line on the xy plane, we can see that it is the projection or shadow of the green line, which is the actual line of intersection of the planes. Now, another way to interpret the meaning of the equation is to say that it is a plane itself containing the orange line and the green line of intersection of the planes. Both ways are perfectly valid, but whichever meaning we use, the equation y equals negative 3/4 x plus 6 cannot be interpreted as the line of intersection of the planes. Similarly, the turquoise line is the intersection of planes 2 and 3, and these are the planes 2 and 3 here. And the actual equation of the turquoise line is just as complicated as the other one. And when we added equations 2 and 3, we got this blue equation, and again this is not the line of intersection of the planes 2 and 3. So as before, I'm going to say that this is a line in the xy plane with a gradient of negative 3 and 15, and a y-intercept of 15. Here is the intersection of the planes 2 and 3, and this is its projection onto the xy plane. Here we see both projections onto the xy plane. Now P is the actual point of intersection of all three planes, and we can see that Q is the projection of P onto the xy plane. So to find the intersection point of the three planes, we eliminated z from equations 1 and 2 to obtain the orange equation. We eliminated z from equations 2 and 3 to get the blue equation. Then we solved these two equations to find x and y. This means that instead of using the actual lines of intersection of the planes, we used the two projected lines of intersection on the xy plane to find the x and y coordinates of the intersection of the three planes. Finally, we substituted these values into one of the plane equations to find the z value.